All right, another one from heat transfer. Could you help me understand why the max heat flux in this scenario is given by HI, the inside film coefficient, times the delta T, T inside minus T dP, which is dew point? I'm having trouble conceptualizing why this represents the maximum heat transfer we're concerned with in this system. I was able to accurately work through finding R total and the dew point temperature, but fell short when I needed to determine the Q value needed to solve for K. So this problem was a pretty interesting problem. It kind of stacks two concepts together. It's truly a heat transfer problem because it's a composite wall of sorts. It's a skylight, and there's two layers of glass with some air in between, and then there's films on both sides. So it's a rich composite wall arrangement already. And then the twist in the problem is that it also has a psychrometrics aspect to it. And it sounds like, from the way this question is phrased, that you're good with the heat transfer aspects of the problem, the composite wall setup and dealing with the resistances and all of that. But the interesting piece was really right at the beginning of the problem when we make the claim, the conjecture that the maximum heat flux is dictated by the delta T between the inside temperature and the dew point temperature of the air. And this is kind of understandable because this is from the TFS program, and you don't have the luxury when you get to the heat transfer section of having done an entire chapter on psychrometrics problems. We do a little bit of psychrometrics in the supporting topics chapter for TFS, but the HVAC folks who encounter a problem similar to this in their program have done almost 20 psychrometrics problems. So this is a fair question for someone that hasn't reviewed psychrometrics in a while, but let's talk about it. So that first layer of the composite wall, I'm not going to redraw the whole composite wall, but just to think about that first layer, we have an internal temperature of 70 degrees, dry bulb, and we have a relative humidity of 60% RH. So that's a fully defined state. And we can find the dew point that's associated with that fully defined state. That's going to be 55.6. I'll put dP for dew point. And if we think about what's happening psychrometrically, that inside air, we'll call that state 1, we'll just arbitrarily put a point here. Some of that air is going to come into contact with the inside surface of that glass, and the glass is going to be colder. So that's going to cause it to cool. And as it cools, sensibly cools, it moves horizontally to the left. So the humidity ratio isn't changing because it's a horizontal line. So no change in the humidity ratio as the dry bulb temperature is reduced as we move to the left. But the relative humidity, these curves here, it's getting higher and higher, closer and closer to 100%, with the end result of getting all the way to the saturation curve, at which point the relative humidity is 100%, and the dry bulb temperature, the wet bulb temperature, and the dew point all converge at the same number, which is this 55.6, if it's allowed to go that far. If it goes any farther than that, then it has no choice but to slide down the curve, and that means that dehumidification will occur. Moisture will be stripped out of that air. Or to say the same thing differently, condensation is going to form. And that's really what this problem is about, is preventing condensation from forming on the glass. So the inside surface temperature of that glass cannot be allowed to get any colder than this. And so we can start the problem by making the statement that if this is the heat flux, we're going to do HA delta T, and then the area was not given. So we're going to, instead of doing total heat transfer, we're going to divide by area on both sides, which we show in the solution. So the rate of heat transfer per unit area then is little q dot, the heat flux, is going to be H times delta T. What is H? Well, H is going to be HI, the inside film coefficient, because it's the boundary between the ambient air inside the room and that first surface that it hits, which is the inside of that glass. And that was given in the problem statement. And then the delta T is going to be the inside temperature, 70 degrees, minus the dew point temperature. I'll call it TIDP. And that dictates the maximum heat flux. If the heat flux were any, the only thing, this is known, this is fixed. The only thing that would make the heat flux larger would be if this delta T was larger, which it cannot be allowed to be any larger than that because this is known and this is the corresponding dew point temperature for this condition. So that has to go there. And that's how we define the maximum heat flux. And then the whole rest of the solution comes out of that. And we go through and we deal with the layers of the wall and the total resistance and the whole rest of that process. So hopefully that addresses it. Sometimes that happens where and what I like about this question is that it illustrates that you can know 90% of everything that there is to do in a problem because you've built yourself up step by step. But there's one missing piece or one thing that you're stuck on or one critical assumption, something that kind of happens early in the problem that keeps you from going forward. And that happens all the time. So you just got to do what you can and focus in on the aspects of it that are confusing. And that's why this is kind of a perfect question. And I'm not surprised at all that it's coming out of the TFS program because like I said, there's no psychrometrics before this. And then you get hit with this dew point thing. No big deal for the HVAC folks that just crush this section, but hard for the TFS folks that aren't really going to get as much emphasis on psychrometrics until supporting topics. And even then, it's a light touch, rightfully so.
That does make sense. Thank you, Dan.
Awesome.